Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 2 of our unit semiconductor. So let's begin with today's class. In today's class we are going to discuss about the two various categories of the semiconductors. One of them is the intrinsic semiconductors and the another is the extrinsic semiconductor. So let's begin with the intrinsic semiconductors and let's have a look what are the types of the semiconductors. First, that it's a types of the semiconductors. One of them, it's an intrinsic semiconductors, and another, it's an extrinsic semiconductors. When I say intrinsic, it is a pure semiconductor which is free of impurity. That is what we call as the intrinsic semiconductors, such as the silicon, atomic number 14, or the germanium, atomic number 32. And when we add a semiconductor with suitable impurity, that is what we call as an extrinsic semiconductors. Extrinsic semiconductors are of two types. One of them is the p type and another one is the n type. So first we are going to begin our discussion with the intrinsic semiconductors. Let's have a look. So for the intrinsic semiconductors, these are the pure semiconductors, and when I say pure semiconductors, that means we have not added any impurity into that semiconductors. So the atoms of pure semiconductors are here. It is the case of the lattice of the germanium has been shown, and as you can show the crystalline structure of this germanium atom, that sorry, it can be seen that a germanium, as it is the Ge32. Yes, so it is having four electrons in its last shell, and this you can see that this one is the valence electrons, and it is going to form covalent bond with its nearby germanium atom, and each covalent bond is going to share two valence electrons, one from each germanium atom. So if you see this bond between this germanium and this germanium, that they are going to use this one atom. If this germanium is also making a bond with this, that it is going to be having with this that one electron has been shared with this, another electron has been shared with this, one electron has been shared with this, and other germanium 2 would be here. So if you take a case of this germanium, it is going to have a four covalent bonds, one with this, another with this, another with this, with this. So basically the four valence electrons in the last shell is being used to form a covalent bond, and when they form covalent bond, they don't have any conduction electrons which we require. Because why we use a semiconductors, that is the biggest question. That if you understand and if you want to clear the concept, always think why to use a semiconductors. Because if your answer is that, sir, because we want a conduction, then my question is, we are having the conductors in nature, and conductors can conduct a lot more than the semiconductors. If your answer is, sir, we want a resistivity from the semiconductor, my answer to you is that we have the insulators, and these insulators are having much higher resistivity as compared to the semiconductors. So why to choose a semiconductors? Always keep asking yourself, and you will find the answer why we are modify this semiconductors. Yes, so please keep this in mind and understand that germanium is there. What we think that let's try the semiconductors, and when we think let's try the semiconductors, we understand that let's use the germanium first, and we have taken a germanium from the nature. And when we take the germanium from the nature, we understood that that all of its valence electrons are having the covalent bond with each of its neighbor, and we don't find any free electrons which can conduct for me. because when we thought that let's use semiconductors, what we want is that electron should flow or current should be flowing through the circuit when I want, and electron or current should not be flowing when I don't want. So basically it is the controlled flow of electrons is required from the semiconductors. Yes, that is why we use this, or that is why we choose this, or we were trying to use convert this semiconductors into a region that it can provide me a controlled flow. When I say controlled, it means when I want it should flowing, when I don't want it should stop flowing. So this is the basic requirement. Let's come back to this. At 0 Kelvin temperature, as you can see, valence band is completely filled with the valence electrons, and the conduction band is completely empty. As you can see this, that valence band is completely filled, as well as you can see this, that every configuration has different pattern. Yes, because no two electrons can have same pattern, can have same energy level, can have same status as the previous one. Yes, and as you can see, one more thing, that it is completely empty conduction band. There is no one who can conduct. So an intrinsic semiconductor can act or is acting as an insulator at the 0 Kelvin. So now if we increase the temperature, as temperature increases due to thermal energy, covalent bonds between atom starts breaking, and electrons in the valence band get energy, and when they get energy they jump into the conduction band. Then the valence band, a vacancy is created because that electron has been jumped from valence band to the conduction band, and this vacancy or deficiency of electrons in the valence band is what we call as the hole. A hole behaves like a positive charge carrier because basically it is the deficiency of electron. So if electron were there, it was negatively charged location, but if it is a deficiency of electron, so no negative is there, that means when no negative is there, it means it is a positive. So that's why we call hole is considered as a positive charge and moves only in the valence band, giving the hole current that generally we denote it by the IH. So the excited electron, as you can see this, that all the electrons were lying over here at 0K, and when we increase the temperature, this electrons has been jumped to this. Yes, so as this electron has been jumped to this, they have created a vacancy, or we can say deficiency of electrons, and that is what we call as the hole. So this is the conduction band, this is the valence band, and this is the intrinsic semiconductor at temperature which is greater than 0 Kelvin. So when an external electric field is applied, you can see this, that there are two different elements, and here when the switch is being pressed, you can see this, as initially the switch is open, and then when we close the switch, that means this circuit has been connected and this circuit has been connected. That means when an external electric field is applied, the valence electrons and hole moving in opposite directions, and this will constitute a current flow through the germanium crystal. I hope this is clear. Is it clear? So great. So if we look at the semiconductor, or I should say intrinsic semiconductor, according to the numbers, let's have a look. So that in intrinsic semiconductors, the number of electrons that we call as a Ne in the conduction band are exactly equal to the number of holes that is it has developed in the valence band, because in reality it is only that this electrons was initially here, then we provide them an energy. When I say energy, we just increase the temperature, that is the form of thermal energy that we have provided, and this electron has been jumped from this to this. That means a whole electron is available at here and hole has been developed. So for intrinsic semiconductors, it is the Ne is equals to Nh. When I say Ne, it is the number of free electrons in unit volume. And when I say NH, it's a number of free electrons, number of free holes in unit volume. Yes, it's a number density basically. So in this semiconductor, the average energy of electrons in the conduction band is always equals to the average energy of holes in the valence band. I hope this is clear. Is it? Great. Now let's discuss the Fermi energy as well. The average of the energies of hole in the valence band and the electrons in the conduction band, that is what we call as the Fermi energy, or we can say the highest energy that an electron can have at 0 Kelvin. At 0 Kelvin is we call as a Fermi energy. The level corresponding to this Fermi energy is what we call as the Fermi energy level. And Fermi energy level in this intrinsic semiconductor is at the middle of the forbidden gap. Let's have a look. So this is the conduction band, this is the valence band, and this is the Fermi energy level between these two levels, and it is at the middle of this conduction band and valence band for the semiconductors, or I should say it's an intrinsic semiconductors. The conductivity of intrinsic semiconductor is very less, and their conductivity can be increased by adding the impurity to it. I hope this is clear. Yes, so this was all about the intrinsic semiconductors, and or I should say it's a intrinsic, or it's a semiconductor at its purest form. Now let's look at certain quick questions. First, in an intrinsic semiconductor, the responsible charge carriers, yes, they are the electrons only? No. Holes only? No. Yes, they are the both electrons and holes, because for the semiconductors it was the case of NH is equals to Ne. Second, a hole is a positively charged electron? No. An unfilled covalent bond? No. An excess electrons in covalent bond? No. It's a missing electron. Yes, it's basically a deficiency of electrons in the valence band. That is what we call as a hole. Next, the intrinsic semiconductors behaves as an insulator at 0 Kelvin. Yes, as soon as temperature increases, it starts conducting. Yes, so this was all about the intrinsic semiconductors. Now we will look for the extrinsic semiconductors. So let's have a look what extrinsic semiconductor mean. When we say extrinsic, we are going to use the doping. And what doping is? It is the process of adding impurities to pure semiconductors to increase their conductivity. That is what we call as a doping. Yes, so extrinsic semiconductors are the semiconductors with impurities, and this extrinsic semiconductors are of two type. One of them is the P type, another one is of the N type. When we say P type semiconductors, so it's when a trivalent impurity, when I say trivalent, it is also known as the acceptor impurity, or group 3 elements like barium or aluminum, or are added in sufficient quantities to the pure form of silicon or germanium crystals, then the resulting crystal is called as the p-type semiconductors. As you can see that one of the barium element has been added to the crystal, and when one of the barium element has been added to the crystal, this is boron, my mistake. Yes, when one of the boron, or even it could be the case of the aluminum, yes, when they are added as a group 3 elements, That means it is having only 3 valence electrons at its outermost orbits. So what are supposed to doing this, that one of the one of the electron will form an covalent bond with this, another has with this, and another covalent bond with this germanium atom. But the fourth one with this, it wants to form a covalent bond, but it does not have any electron or in the outer shell. So there is a deficiency of electron, and that deficiency of electron is known as the hole. So this is the trivalent impurity atom, and each impurity atom has sorry, each impurity atom has 3 valence electrons, and these electrons form 3 covalence bond with the neighboring silicon or germanium atoms. This fourth covalent bond is incomplete or empty, and due to this deficiency of electron, a hole is created. Therefore, excess holes in addition to those formed due to thermal energy are available for conduction in the valence band, and hence the conductivity of the semiconductor is increases. So in the n-type materials or p-type semiconductors, holes are the majority charge carriers and electrons are the minority charge carriers, and we can say it's an NH much greater than Ne, because NH plays as a majority charge carrier when we talk about the p-type semiconductors. And always understand that this is electrically neutral, this is not positively charged, because whatever the number of holes has been created, that is because of deficiency of electrons, and that electrons are already in the conduction bands. So this is not positively charged, it is always electrically neutral. And when we want the relation among the electron density or the hole density, then the density of intrinsic charge carriers, which is equals to NH into Ne, would be equals to Ni square. So this is NH into Ne is equals to Ni square for the extrinsic semiconductors. I hope this is clear. And one more thing, the Fermi energy level, as you can see this, the Fermi energy level shifts near to the valence band because there are more number of electrons are available at the valence band because of creation of this holes with the help of acceptor type impurity or group 3 atoms. So as you can see this, that's why forbidden energy gap or the forbidden energy level has been shifted, which was in the intrinsic semiconductors at the middle of them, at the middle of the conduction band and valence band. Is it clear? Is it? Great. Now let's look what happens when we want to form an n-type semiconductors. When we want an n-type semiconductors, we choose a pentavalent impurity, or we can say it's a donor impurity, or it's a group 5 elements like phosphorus or arsemony or bismuth, etc., are added in sufficient quantities to the pure form of silicon or germanium crystal. And due to this this resulting crystal, that is what we call as the n-type semiconductors. As you can see this, one of the fifth group element has been added as an impurity to the germanium crystal, and when this all are the fifth group elements, that means they are having the 5 valence electrons in their outermost shell. Within that 5, you can see this one covalent bond with this, another covalent bond with this, another covalent bond with this, another covalent bond with this, and one excess amount of electron, which we call as a free electron, is available. So each impurity atom has a 5 valence electrons, and out of this 5 valence electrons, 4 electrons are needed to form covalent bonds with the adjacent germanium or silicon atoms, and the fifth electron is very loosely bound, and it needs a less amount of energy to become a free electron. Therefore, this excess amount of electrons are available for conduction, and conductivity of semiconductor increases. We can say electrons are the majority charge carriers, and holes, they are the minority charge carriers here. That means Ne, the number of free electrons, is greater than the number of free holes. And again, this n-type material is electrically neutral, and in this case the Fermi energy level shifts near to the conduction band. The relation between the electron density and the hole density and the density of the intrinsic charge carriers could be given as Ne into Nh. Ne into Nh, that would be equals to approximately equals to Ni square. You can see this conduction band, that in this situation the Fermi energy level has been shifted in the upward direction as it was in the middle one. Yes, so this is due to the donor level. It's a one more one electron, or I should say one more free electron is available. That's why we are having the free electrons current over here. So this is the diagram of semiconductor conduction n-type semiconductor for the conduction band and valence band. Let's understood that conductivity of n-type is greater than the conductivity of p-type, or we should say greater than of intrinsic semiconductors. So with the increase of the temperatures, the ratio of Ne is to Nh for n-type decreases. But Ne is to Nh, which should be a greater than 1. Or with the increase of temperature, the ratio of the Ne divided by Nh for p-type increases, but Ne by Nh is less than 1. So whenever a covalent bond breaks, an electron hole pair is formed, and that is what we required is, yes, that intrinsic semiconductors were there. When we used to have intrinsic semiconductors, they are the one which does not conduct at all. Now the situation is that we have found a certain approach, so that with the help of that we can at least conduct something. Yes, so when I say we can have conduction of something, because when we say that we are going to add the impurities, so what is the amount of impurities that we add? Do you know this? What is the amount of impurity that we add? Generally we add the impurity, it's 1 ppm. When I say ppm, you understand that it's a parts per million. So one atom of an impurity, either it could be of p type or it could be of n type, but 1 parts per million parts of the intrinsic lattice is going to be add with this. And when only 1 parts per million is going to add for this, you may understand that the situation is that only a very little amount of holes or very little amount of electrons it could be generated, but at least something is better than nothing. When we were using the intrinsic semiconductors, we don't find anything, that almost zero current, and almost they behave like a insulators if we talk about the 0 Kelvin. Now with the addition of this impurities, at least we find that certain current can flow. Either it could be due to holes, or either it could be due to electrons. So we are achieving something, and this journey will continue. I hope this is clear. What was our prime motive is that when we use semiconductor, we want a controlled flow of currents. Controlled flow, I mean, when we should achieve a current. When we don't want, a current should be cut off. So at least we find that how the current can flow. At this point of time, we don't know how to control that flow of current, but at least we find that how to flow the currents. I hope you understand this. So let's have certain quick questions. Adopt semiconductor is positively charged? No. Negatively charged? No. It is electrically neutral. Yes, please always do remember this, because we are going to tempted it by positively charged or negatively charged by saying that if it is a p-type impurity, it's a deficiency of electrons, and when it is a deficiency of electrons, that means more positive ions, and more positive ions, that means positively charged. I have found many students who are making this mistake. Please, you people, do not commit this mistake. Next question. An N-type and P-type silicon can be obtained by doping pure silicon with arsenic and phosphorus? No. Indium, aluminum? No. Phosphorus and indium? Yes. These are the different elements. And aluminum and boron? No. I hope this is clear. Third one. The Venn diagram of three semiconductors are given in the figure. From left to right, they are respectively. Yes. Conduction band and valence band, and the Fermi energy level has been shifted upward. This is conduction band, this is valence band, and Fermi energy level is almost at the middle. And conduction band and valence band and Fermi energy level is the downside. Yes, so this would be the N type. This is intrinsic because it is at the midway, and this is near the valence band, that means this is P type. I hope this is clear. So N intrinsic and P type. I hope this is clear. Is it? Correct. So let's wind up the session over here. This was another theoretical session. Yes, but up till until we can conduct the currents through this, it is all about the theoretical session. But this theories are much interested, and the second thing is this is having a higher probability to be asked in the questions in the exam. So please revise this lectures as well as NCRT also. Please, that is recommended. Please do it. Thank you. Have a good day. Take care.